Hello and good afternoon friends, welcome once again to the CEC-UGC live lecture. Dear friends, I would like to tell you all that today we are going to discuss once again for our series Chemical Reaction and Mechanism. I would like to tell you all that as you also know that we are carrying this series Chemical Reaction and Mechanisms, and under this very series we have conducted numerous sessions. This is the 7th lecture in the series, and today in this lecture we are going to discuss about the reactions of aldehydes and ketones, and for this we have again with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Thiols College, University of Delhi. So taking advantages from her experiences as well as the way she used to deliver her lectures through our EduSet platform, I hope that this lecture is going to be one of the exciting as well as one of the productive sessions, and you would be going to learn more and more, which sometimes you tend to skip while reading your books. So over to you ma'am again, and as I already said, this is the series based lecture. So now today it is for the reactions of aldehydes and ketones. So over to you ma'am.
Thank you so much ma'am. Good afternoon everyone. Welcome to the series of Chemical Reactivity and Mechanism. As you know, in the last lecture we have taken the very important functional groups aldehydes and ketones. We have discussed what are the aldehydes and ketones and what are their preparations. Today we will come to the next point, the reactions of aldehydes and ketones. You know what are aldehydes and ketone? Aldehydes and ketones are carbonyl compounds. Both the aldehydes and ketones having carbonyl group. In aldehydes, one group may be alkyl group, aryl group, alkenyl group, any group with hydrogen. And in ketones, the carbonyl compounds with alkyl group, aryl group or alkenyl group. When we come to the point reactions of aldehydes and ketones, the most important point comes my mind from carbonyl group. What is carbonyl group? C double bond O. One bond is sigma, another bond is pi bond. So this particular carbonyl group is responsible for all kind of chemical reactions. As we know what is electromagnetic effect, that when in presence of any attacking reagent, there is a temporary shifting of pi electrons towards more electronegative atom, and in carbonyl group, as we are aware that oxygen is the more electronegative atom as compared to the carbon. So reaction, when we are talking about the reactivity of aldehydes and ketones, aldehyde and ketones gives nucleophilic addition reactions, and nucleophilic addition reaction basically just due to the shifting of pi electron, temporary shifting of pi electron towards more electronegative atom, that is oxygen atom as compared to carbon. So we are continue this topic aldehyde and ketones. They may also known as alkanals, we have discussed earlier, and alkanones. What are the main thing about the reactions? The aldehyde and ketones are mainly due to the carbonyl group. The functional group of these compounds, the carbonyl group is highly reactive because of the presence of a polarized pi bond between carbon and oxygen. The numerous reactions given by aldehyde ketones can be categorized in 5 points. Number 1, nucleophilic addition reaction, nucleophilic addition elimination reactions, oxidation reactions, reduction reactions, and reactions involving alpha hydrogen of the carbonyl group. You can see the resonance structure of carbonyl group. In presence of attacking reagent electromagnetic, due to electromagnetic effect, there will be a partial negative charge on oxygen and partial positive charge on carbon, and because of its partial positive charge is subjected to nucleophilic attack by a variety of nucleophilic reagents. What are nucleophiles? Any negatively charged species or atom or electron rich species. A nucleophile attacks the carbonyl carbon from a direction which is not exactly perpendicular to the plane of the carbonyl group, but sustain an angle of about 107 knot to the carbonyl bond. As the nucleophile forms a pi bond to the carbonyl atom with its own electron pair, the hybridization of this carbonyl group changes from sp2 to sp3, that is trigonal to tetrahedral, and the electron pair of the pi bond moves to the oxygen atom. As a result, tetrahedral alkoxide ion is produced. You can see in the reaction that carbonyl carbon is attacked by the nucleophile and an alkoxide intermediate is formed. And this one is pick a proton from either the solvent, reagent, water or acid to give the addition product. So, basically nucleophile simply adds to the carbonyl carbon and we will get the addition product. Relative reactivity of aldehydes and ketones. Carbonyl compounds differ from each other with respect to their reactivity towards nucleophilic addition reaction within a given nucleophilic reagent. This difference can be explained on the basis of electronic and steric effects. What is electronic effect? The electron releasing inductive effect of an alkyl group attached to the carbonyl carbon decrease the positive character on the carbonyl carbon and hence make it less susceptible to the nucleophilic attack. Obviously, the reactivity of carbonyl compound would be in decreasing order with the increase in the number of alkyl group. Hence, as the alkyl group increases, the reactivity of carbonyl compound will be decreases. An aryl group bonded to the carbonyl carbon also decrease the reactivity of carbonyl group even more than alkyl group because of delocalization of positive charge of carbonyl group by resonance. For this reason, we can say that aromatic aldehydes and ketones are less reactive than aliphatic aldehydes and ketones. Thus, we can expect a relative order of reactivity as shown in the order. The more the aryl group, the reactive will be the less as compared to the aliphatic. On the other hand, an electron withdrawing substituent, particularly when attached to the alpha carbon, will increase the reactivity of carbonyl carbon by increasing the positive charge of the carbonyl group. You can see that the order of the compounds, when chlorine atom is added to the alpha carbon, the reactivity is increasing because of its electron withdrawing nature. What is a steric effect? You know, crowdedness. Steric means crowdedness. More the bulky group, more will be the steric effect. The reactivity of the carbonyl group in addition reaction is also influenced by the size of the substituents bonded to the carbonyl carbon. When addition occurs, the substituents are pushed back closer to one another because the hybridization changes from, as we are aware, sp2 to sp3 in the product, and the bond angle changes from 120 to 109.5 degree. The bulky alkyl or ergyl group attached to the carbonyl carbon lead to a more crowded situation in the addition product, and this causes the reversible addition reaction to go neither very fast nor very far. As a result, the increasing size of the substituent decreases the reactivity of aldehydes and ketone, and the addition product also reduces. So, we can say the relative reactivity of the compounds as follows: more the crowdedness, less will be the reactivity of a aldehyde or ketone. What about cyclic ketones? Cyclic ketones almost always react more rapidly than acyclic analogous because alkyl group in acyclic carbon compounds have considerable more freedom of motion and produce greater steric hindrance in the addition product. On the other hand, methylene group of cyclic ketones are tied back through ring formation. This reduces the steric interference to a large extent. First of all, we will discuss the addition of water. When water added to the aldehyde or ketone, we get the hydrates, and hydrates are also known as jam diols. What is gem? Means hydroxyl group attached to the same carbon atom. The addition of water to the carbonyl group of the aldehyde and ketones is a reversible reaction, and the equilibrium in most cases lies on the left. The reaction is endothermic, means energy is absorbed and energetically unfavorable. An aqueous solution of formaldehyde consists of 99.9% diol, but for acetone it consists only 0.1% gem diols. You can see in the reaction that formaldehyde when reacts with water in nucleophilic addition give formaldehyde in 99.9% and acetone will give 0.1% only. Certain aldehydes and ketone containing a electron attracting group from hydrates of sufficient degree of stability to permit their isolation. Two examples are chloral. What is chloral? It is trichloroacetaldehyde and hexafluoroacetone. These compounds are destabilized by very strong dipole-dipole repulsion between carbonyl carbon and trihalomethyl group. They achieve stability by destroying the carbonyl group by the formation of hydrates. In the hydrate, the carbonyl group dipole is replaced by much weaker dipole of the diol. The hydrogen bonding between hydroxyl group and halogen atom is the another factor that stabilizes the hydrates. You can see in the reaction that chloral with nucleophilic addition of water give chloral hydrates, which is less dipole, having less dipole repulsion, and in hexafluoroacetone strong dipole repulsion is reduced by hydrate formation. Cyclopropane can also form stable hydrate because on addition of water angle strain of the ring is released up to some extent, and there is a conversion of sp2 hybridization of carbonyl carbon to sp3 in hydrate. Glyoxal and ninhydrin also form stable hydrates. You can see in the reaction that cyclopropane gives cyclopropane hydrate and ninhydrin give hydrate of ninhydrin. These are the structures of these two compounds. Next reaction, addition of hydrogen cyanide HCN. Aldehyde and unhindered ketones react with hydrogen cyanide in weakly basic media to produce gem hydroxycyanides, usually called cyanohydrins. The reaction involves addition of hydrogen cyanide to the carbon oxygen double bond. The function of base to generate the active nucleophile, that is cyanide CN negative from the weak acid HCN. So, we required a base for this reaction. The nucleophile now can simply attack to the carbonyl carbon from either side. When we are saying that either side, definitely there is a enantiomer product. So, when acetaldehyde react with hydrogen cyanide, enantiomers will get enantiomers. You know what are enantiomers? These are the isomers of the same structure formula and difference in the rotation of the optically light. So, 2-hydroxypropane nitrile or acetaldehyde cyanohydride, we can nomenclature by both the ways. Acetone when react hydrogen cyanide to give 2-hydroxy 2-methyl propane nitrile or acetone cyanohydrin. Hydrogen cyanide is highly toxic, we are aware of it. So, what we can do, we can take the sulfuric acid to a mixture of carbonyl compound and aqueous sodium cyanide, so that hydrogen cyanide will remain in C2. The reaction is base catalyzed, hence the amount of acid added should be insufficient to consume all the cyanide ion, so that a weakly alkaline condition is maintained by rapid addition. The hydrolysis of unreacted sodium cyanide maintains the alkalinity. By this reaction, you can see sodium cyanide when reacts with water, it will give you sodium hydroxide to maintain the alkalinity. and sterically hindered ketones such as diisopropyl ketone, di-tertiary butyl ketone and diaryl ketones practically do not form cyanohydrins because of steric hindrance, and alkyl aryl ketones give poor yields. Cyanohydrin formation is synthetically useful because of the subsequent reaction that can be carried out. For example, acid catalysis hydrolysis of cyanohydrin gives an alpha hydroxy carboxylic acid, which on reduction with lithium aluminum tetrahydrogen or with catalytic reduction gives a primary amine with an hydroxyl group at the beta position. So, in the reaction acetaldehyde cyanohydrin on hydrolysis in heating will give you 2-hydroxypropanoic acid. Benzaldehyde will give you first of all benzaldehyde cyanohydrin with the reaction of hydrogen cyanide, and further two reactions are there. First, when reduced it will give you 2-amino 1-phenylethanol, and when hydrolyzed it will give you mandelic acid. This is the mechanism of the addition of hydrogen cyanide in alkaline medium. First of all, hydroxyl ion will react with hydrogen cyanide to produce the active nucleophile. We have already stated Cn minus. This nucleophile then attack to the carbonyl carbon, and then there is a formation of enantiomer, then there is a attacking of hydrogen ion on the oxide ion, and then we will get the acetaldehyde cyanohydrin. So, basically in this reaction first of all we have produced an active nucleophile, and this active nucleophile then attached to the carbonyl carbon acetaldehyde, and this is the way we get the cyanohydrin of acetaldehyde. Addition of sodium bisulfite. Aldehydes, methyl ketones and sterically unhindered cyclic ketones when treated with a saturated aqueous solution of sodium bisulfite form the addition product with bisulfite. Solution and are obtained as crystalline solid. Most other ketones do not form bisulfite addition product because the addition reaction is reversible and very sensitive to steric hindrance. You can see in the reaction that there is a nucleophilic addition to the acetaldehyde. Why it is attached to with the sulfur? Because it is act as a nucleophile with the lone pair of electron, and then there is a proton transfer, and we will get the bisulfite adduct, the addition product. Same acetone will react with sodium bisulfite, nucleophilic addition reaction will be there followed by proton transfer again, and you will get the addition product sodium 2-hydroxypropane 2-sulfonate. When cyclohexanone ketone, cyclic ketone reacts with sodium bisulfite, you will get the product sodium 1-hydroxy cyclohexane sulfonate. So, again there is a nucleophilic addition of sodium bisulfite. The carbonyl compounds can be regenerated from the addition product by simply heating with dilute HCl or alkali. Therefore, the reaction affords a convenient means of separating aldehydes and ketones from non-carbonyl compounds. The reaction shows the difference between aldehydes and ketones from other carbonyl compounds, non-carbonyl compounds. Sodium bisulfite addition compound on being heated with sodium cyanide forms cyanohydrins. Thus, it avoids the use of toxic hydrogen cyanide for the preparation of cyanohydrins from aldehydes and ketones. Next reaction is the addition nucleophilic addition of Grignard reagent. You know what are Grignard reagent? We have discussed in previous lecture. These are MgX, alkyl or aryl group with magnesium and halide ion. Aldehyde and ketones undergo nucleophilic addition with Grignard reagent in anhydrous ether or tetrahydrofuran to form halomagnesium alkoxide as addition product which on acidification with the dilute acids yield alcohols. Formaldehyde gives primary alcohol, other aldehydes gives secondary alcohols, and ketone gives tertiary alcohols. Examples are here. First of all, we are taking the formaldehyde. When reacts with methyl magnesium iodide, it will attack as nucleophile and we will get the addition product with the Grignard reagent, and then hydrolysis will give you ethyl alcohol, or we can say it is a 1 degree alcohol. With acetaldehyde, first of all there is a addition product which on hydrolysis will give you 2 degree alcohol, that is butane 2-ol. Ketone butane 2-on with phenyl magnesium bromide will give you first of all addition product, nucleophilic addition product. Then hydrolysis will give you the 3 degree alcohol, that is 2-phenyl butane 2-ol. So, we can differentiate the aldehydes and ketones with the addition of Grignard reagent to the aldehydes and ketones. A hindered ketone does not undergo nucleophilic addition with a hindered Grignard reagent. Instead, it is reduced by the Grignard reagent possessing a hydrogen on alpha carbon to a secondary alcohol. The Grignard reagent is converted to an alkene. For example, if we are taking the reaction of diisopropyl ketone with isopropyl magnesium bromide, it will give you diisopropyl carbinol and propene. There is a rearrangement of the compound. Addition of the organolithium compound and acetylide ions. Organolithium reagents are more reactive than Grignard reagent, and this enables them to undergo nucleophilic addition even with the hindered ketones that could not be happen with the Grignard reagent. So, the product obtained after acidification of the initial product is an alcohol. These are the reactions to form the organolithium compound. Then sodium alkynides prepared, then this organolithium compounds when reacts with hindered ketones will give you the alcohol. Sodium alkynides prepared from terminal alkynes by reaction with sodium amide in liquid ammonia also undergo nucleophilic addition with aldehydes and ketones. The product is an alcohol with carbon double bond carbon at the adjacent position. So, you can see that sodamide when reacts with propyne, it is a terminal alkyne because triple bond of alkyne is on the terminal position. It will give you sodium propionide first of all, and then we will get the alcohol. This is pent 3-ine 2-ol on hydrolysis of this addition product. Next reaction is the very important reaction 1,2 and 1,4 addition of nucleophiles to alpha beta unsaturated aldehydes and ketones. Alpha beta unsaturated carbonyl compound exhibit resonance. As shown in the figure, the resonating structure of alpha beta unsaturated carbonyl compounds. In alpha beta unsaturated carbonyl compounds, the carbonyl carbon and the beta carbon are both electrophile. So, a nucleophile can attack either of these positions. When the nucleophile attack the carbonyl carbon, finally an 1,2 addition product is obtained because we are considering oxygen 1 and carbon 2 after protonation of initial product of the addition. This is an alkoxide. The final product is an alcohol possessing a double bond at the adjacent position. So, we can say it is 1,2 addition product. In the reaction, you can see that nucleophile first of all attack on the carbonyl carbon, which is alpha beta unsaturated, then there is a addition product, and after hydrolysis the product is 1,2 addition. The double bond is in alpha beta positions. On the other hand, when the nucleophile attacks at the beta carbon, the enolate is formed, which on protonation gives an unstable enol. This addition is called 1,4 addition. The enol tautomerizes to more stable keto form, a saturated aldehyde or ketone. The overall result of 1,4 addition is the addition of nucleophile and hydrogen atom across the double bond that was conjugated with the carbonyl group. For this reason, it is called 1,4 addition, the conjugate addition. You can see in the reaction that first of all nucleophiles attacks on beta carbon, then it hydrolysis to give enol form, which is tautomerizes to keto form, and finally it is the 1,4 addition, conjugate addition. Grignard reagent commonly undergo 1,2 addition with simple alpha beta unsaturated aldehydes, whereas alpha beta unsaturated ketones undergoes 1,4 addition. In the reactions you can see the but2 enol when reacts with Grignard reagent, phenyl magnesium bromide followed by hydrolysis to give 1-phenyl but2-ene-1-ol, a addition product, 1,2 addition product, where we have discussed in the last slide that 1,2 addition product will be formed with aldehyde and minor product of 1,4 addition. This is 3-phenyl butanol. Ketones when reacts with phenyl magnesium bromide followed by hydrolysis will give you again the addition product, but the difference is that 1,4 addition will be the major product. This is your 4-phenyl pentane 2-on, and 1,2 addition will be the minor product. This is your 2-phenyl pent 3-ene-2-ol. Organolithium nucleophiles mainly undergo 1,2 addition, whereas organocopper nucleophiles undergo 1,4 addition almost exclusively. For example, when 1,3-diphenyl prop 2-ene-1-on reacts with organolithium followed by hydrolysis will give you the major product 1,2 addition. So, here is the example. The product is 1,1,3-triphenyl prop 2-ene-1-ol and the minor product is 1,3,3-triphenyl propane 1-on. The another example is when organocopper reacts with ketone, that is 3-methyl cyclohex 2-enone, it will gives you 1,4 addition product preferentially, and this is your 3,3-dimethyl cyclohexanone. So, we can differentiate. Next important reaction is nucleophilic addition with elimination reaction. Aldehydes and ketones react with several derivatives of ammonia, we can say H2N. In weakly acidic medium, it should keep in mind that medium should be acidic to form at first addition product, which is known as carbinolamines. The later under the reaction conditions spontaneously eliminates a molecule of water to form the ultimate products containing carbon nitrogen double bond, that is known as imines. You can see in the reaction that aldehyde and ketones when reacts with derivative of ammonia, first one hydrogen is replaced by the group Z. That is why it is known as the derivative of ammonia. The product first form is carbylamine, and it hydrolysis by elimination of water molecule it will give you N substituted. Why N substituted? Because the substituted group is attached to the nitrogen. So, N substituted imine C double bond N will form. The Z substituted group may be alkyl group, aryl group, hydroxyl group, NH2 group, NHC6H5, NHC6H3, NO2 का whole twice and NHCO, NH2. These groups may be substituted to the ammonia. So, a number of products can be obtained by this reaction, the very important reaction, nucleophilic addition elimination reaction. Mechanism as far as concerned, these reactions are catalyzed by acid. Very important point, we should keep in mind that reaction medium should be acidic. Acid protonates the carbonyl group at the oxygen atom. In the reactions you can see that proton will add to the oxygen. This increases the electrophilicity of carbonyl carbon so that weak nucleophile, this is your substituted ammonia, can add to the carbon oxygen double bond. The acid can also catalyst dehydration of carbonylamine by increasing the leaving group ability of hydroxyl group through its conversion to the better leaving group, that is protonated water molecule. However, if the acid concentration is too high, the nucleophilic reagent will be converted to the non-nucleophilic compound, this is N positive H3Z. So, we should keep in mind the acidity should maintain, but the concentration should also maintain. So, the addition product will not take place. The reaction occurs best when the concentration of both the protonated carbonyl carbon and the nucleophile are at the maximum. This is achievable at about pH 4, the very important point, pH should be 4. For this reason, the reaction is carried out in a medium containing sodium acetate and acetic acid. It should be notable. This buffer mixture maintains the pH at about 4. The mechanism is shown in the reaction. First of all, proton adds to the carbonyl oxygen, then there is a attacking of the nucleophile, weak nucleophile becomes easier, then there is a removal of proton to get the carbinolamine, and then there is a removal of protonated water molecules, the leaving ability is increased, and after removal of water molecules and rearrangement you will get the product N substituted imine, the very synthetically very important compounds. Reactions with amines. Aldehydes and ketones react with primary amines to form N substituted imines. This is also known as Schiff base. The very important compounds used in almost all the fields. Catalytic hydrogenation of these imines gives amines. The reduction of imines can also be affected by sodium borohydride and sodium cyanoborohydride, and the overall process is called the reductive animation of the aldehydes and ketones. In the reactions you can see, first of all, acetaldehyde when reacts with methylamine, it will gives you N-methyl acetaldeimine, and on reduction it will give you ethyl methylamine. Benzaldehyde when reacts with aniline, it is first of all give you E and Z, these are the enantiomers, N-phenyl benzaldeimine, and on reduction with sodium borohydride it will give you benzyl phenylamine. Cyclohexanone, a ketone, when reacts with ethylamine, it will gives you N-ethyl cyclohexaneimine, and it on further reduction with sodium borohydride cyanide will give you cyclohexyl ethylamine. Aldehydes and ketones reacts with secondary amines to give enamines. What are enamines? You can see ene plus amine. Enamines can act as a nucleophiles and are useful in organic synthesis to prepare alpha alkyl and alpha acyl ketones as given below. This is called important Stork-enamine reaction. In this reaction, first of all, cyclohexanone when reacts with pyrrolidine will give you an 1-cyclohexenyl pyrrolidine, an enamine, and then synthesis of alpha alkyl and alpha acyl can be seen. When reacts with methyl iodide, it will gives you alpha methyl cyclohexanone, and when reacts with methyl acyl group, it will the acyl group introduced at alpha position in ketones, that is cyclohexanone. Reaction with hydroxylamine, aldehydes and ketone reacts with the hydroxylamine, that is NH2OH, to form oximes, very important reaction, and oximes of aldehydes are called aldoximes, while those with ketones are called ketoximes. The reaction is catalyzed by acid and is best carried out at about pH 4. The acidity of an acetic acid and sodium acetate buffer mixture. So, formaldehyde when reacts with hydroxylamine will give you formaldoxime, acetaldehyde will give you acetaldoxime, acetone will give you acetoxime. So, nucleophilic addition from hydroxylamine on carbonyl carbon takes place, and nitrogen will attach to the carbonyl carbon having lone pair of electron. The oximes are crystalline solid with sharp melting points and are therefore useful for identification and characterization of aldehydes and ketones. So, we are taking this reaction in the practical also to differentiate between aldehydes and ketones. Very important reaction, another Beckmann rearrangement. Ketoximes when treated with an acid catalyzed such as H2SO4 are converted to N-substituted amides. The acid catalyst may be used are H2PO4, P2O5, PCl5, SOCl2, C6H5SO2Cl. The reaction involves migration of an alkyl or aryl group of the functional carbonyl carbon to the nitrogen atom. The group migrates must be anti with its bonding electron pair. This is the notable point in this important reaction. The chiral group migrates the retention of its configuration in the product. So, the reaction is intramolecular and the reaction proceeds by the following mechanism. This is the example of E. Acetophenone oxime on treatment with E and Z basically related to the stereochemistry of alkenes. Antigigan and Juzaman, E for antigigan and Z for Juzaman. On treatment with H2SO4 yields N-phenyl acetamide. In the reaction you can see the mechanism. First of all, acetophenone oxime when reacts with proton to give this proton attack to the hydroxyl group, protonated water molecule is there. Then there is a migration of a group which is anti to this group. The only anti group will migrate, this should keep in mind, and then after hydrolysis and removal of proton, the N-substituted amide, that is N-phenyl acetamide, will produce Z-acetophenone oxime on treatment with H2SO4 gives N-methyl benzamide. You can see in the reaction the linear polyamide, that is nylon 6. It is a synthetic fiber. It is manufactured by the following sequences of the reaction, and this reaction involves the Beckmann rearrangement of cyclohexanone oxime to omega caprolactam, that is a cyclic amide, and then polymerization of this omega caprolactam in presence of a trace amount of water to give nylon 6. So, a ketone cyclohexanone when attacked by nucleophilic addition of hydroxylamine will give you cyclohexanone oxime, and when reacts with H2SO4 it will gives you omega caprolactam. So, there is a ring expansion in this reaction, and after polymerization of this omega caprolactam you will get the fiber nylon 6. So, industrially this reaction is very important. Reaction with the hydrazine. What is hydrazine? NH2 NH2, or we can also say N2H4. When aldehyde and ketones reacts with hydrazine, hydrazones are formed. Formaldehyde when reacts with hydrazine, nucleophilic addition will be there and we will get the product formaldehyde hydrazone. Acetaldehyde will give you acetaldehyde hydrazone, both the product will form E and Z. Acetone when reacts with hydrazine we will get the product acetone hydrazone. So, what are E and Z? We are looking that in some reaction they are E and Z. Basically E and Z related to the stereochemistry of alkenes. If the group attached to this C double bond C alkene group, the groups of higher priorities are reside on same side, it will be Z, same side parallel to this double bond it will be Z zooxamine, and if the groups of higher priorities resides on opposite side it will be E, as we can see in the previous reaction that it is E and it will be Z for acetophenone. So, these are basically related to the stereoisomers of alkene. Reaction with phenylhydrazine. Aldehydes and ketone when reacts with phenylhydrazine will form phenylhydrazones. This reaction is usually carried out in sodium acetate, acetic acid buffer medium will be there and pH will be 4. These are the reactions when for formaldehyde, acetaldehyde and acetones. Formaldehyde phenylhydrazone will be the product with formaldehyde, acetaldehyde phenylhydrazone and acetone phenylhydrazone with acetaldehyde and acetone respectively. Reaction with 2,4-dinitrophenylhydrazine. Aldehydes and ketones when heated with a solution of 2,4-dinitrophenylhydrazine in ethanol containing a small amount of H2SO4 or HCl will form the 2,4-dinitrophenylhydrazones. It is commonly used in the lab and in the short form we are saying it 2,4-DNP derivatives. These are high melting colored solids, yellow, orange or fat. For this reason the formation of 2,4-DNP derivative is used as a positive test for the detection and presence of aldehydes or ketone in given organic compound in the analysis of organic compound. So, you can see in the reaction how 2,4-dinitrophenylhydrazine reacts as nucleophile with the carbonyl group of acetaldehyde and the product will be known as hydrazones. With acetone again there is a formation of acetone 2,4-dinitrophenylhydrazone. 2,4-dinitrophenylhydrazine is known as Brady's reagent. It is a much weaker base than the other derivatives of ammonia. For this reason, the reaction in this case is carried out in relatively stronger acid medium. This reaction with the other reagent as described are carried out in a buffer with pH 4. Reaction with semicarbazide. Aldehydes and ketones when heated with semicarbazide hydrochloride in water containing sodium acetate form semicarbazones. Schiff bases as crystalline solid. Semicarbazone possesses sharp melting point and are thus useful for characterization of aldehydes and ketones. For viewers, I would like to explain about the semicarbazones. These are synthetically very important. These after metallic reaction with semicarbazones, when they react with metal halides or any other anions with metals, there is a coordination compound form, and these coordination compounds are synthetically very important in not only in pharmaceuticals but in other fields also. These are basically used as drugs for many purposes like anti-malarial, anti-cancer, anti-fungal, antibacterial, for dyes. So, these semicarbazones are very important compound, and it is useful for the characterization of aldehydes and ketones. Acetaldehyde when react with semicarbazide, it will give you acetaldehyde semicarbazone, and acetone when reacts with this will give you acetone semicarbazone. Reaction with alcohols. It is also known as the formation of acetals. When aldehyde or ketone is treated with a large excess of an alcohol in presence of trace amount of acid, a acetal is formed. What is acetal? It is a jam dialkoxy compound or diether of a jam diol. So, the aldehydes or ketones at first add a molecule of alcohol to form jam alkoxy alcohol, usually known as hemiacetal, because only one group is attached to it. Then this hemiacetal being unstable reacts further with another molecule of alcohol to form a acetal. The hemiacetal and acetals derived from ketones once called hemiketal and ketals respectively, but these names are no longer used. The acid catalysts that are commonly used are gaseous hydrogen chloride, concentrated sulfuric acid, and para-toluene sulfonic acid. You can see in the reaction how acetaldehyde reacts with alcohol to form hemi and acetal compound. Another reactions for acetones and cyclohexanone. Acetone first of all reacts with alcohol, methyl alcohol, to form 2-methoxypropane 2-ol. Then further reaction will give you a ketal, that is 2,2-dimethoxypropane. Cyclohexanone when reacts with methyl alcohol, 1-methoxycyclohexanol, it is a hemiketal, and then 1,1-dimethoxycyclohexane, a ketal will form. So, nucleophilic addition of alcohol will form in all the cases. All these steps involved in the formation of acetal are reversible. The reaction is driven to the right either by use of excess alcohol or by removal of water in the reaction, or both. Water can be removed by using a desiccating agent such as anhydrous calcium chloride or by azeotropic distillation with benzene. Formation of ketals is much less favorable. Most ketones except acetone and cyclic ketones do not form ketals with monohydric alcohols. However, both aldehydes and ketone readily form 5 and 6 membered cyclic acetals by reacting with 1,2-ethane diol and 1,3-propane diol respectively. So, very important reaction, and reversibility can be changed as we have noted either by use of excess alcohol or by removal of water. So, you can see in the reaction pentane 3-on when reacts with 1,2-ethane diol will give you pentane 3-on ethylene ketal. Cyclohexanone when reacts with 1,2-ethane diol will give you cyclohexanone ethylene ketal, and cyclohexanone when reacts with 1,3-propane diol, the product will be 1,5-dioxa 5,5 undecane. 5 and 6 membered cyclic acetals are formed spontaneously from the corresponding hydroxyaldehydes, and most are stable compound that can be isolated. And you can see in the reaction that 4-hydroxybutanol will give you 2-hydroxy tetrahydrofuran, and 5-hydroxypentanol will give you 2-hydroxy tetrahydropyran. Acetals and ketones are unreactive towards nucleophiles, bases and oxidizing agent. They are easily hydrolyzed back to the carbonyl compounds by treating with dilute aqueous acid. So, acetals and ketones are extremely useful as protecting group for aldehydes and ketones. So, we can see it is very important points for the synthesis of another compound with the help of aldehydes and ketones, that these groups can be protected with these kind of reactions. In a synthetic scheme, sometimes it is necessary to protect the aldehyde and ketone in order to prevent it from reacting with the reagent which is employed for transformation of some other functional group present in the molecule. When the desired transformation has been accomplished, the carbonyl group is regenerated simply by hydrolysis with a dilute acid. Here is an example: the conversion of methyl 4-oxocyclohexane carboxylate to 4-hydroxymethyl cyclohexanone requires the reduction of the ester functional leaving group, the ketone group intact. The problem is that ketone group is more easily reduced than the ester group. So, it must be noticed any reducing agent, for example, if we are taking lithium aluminium hydride, that will reduce the ester group and will reduce the ketone group as well. And you can see in the reaction how the reaction proceed and how the alcohol is formed. If the reduction is carried out without protecting the ketone group, that in spite of having the desired compound, we are also having the mixture of cis and trans 4-hydroxymethyl cyclohexanol will produce. In the reaction, you can see that ketonic group will also get converted to the hydroxyl group. Mechanism of this acid catalyzed acetals or ketal formation, you can see that there is a nucleophilic addition of this alcohol to the carbonyl carbon after the addition of proton to the carbonyl oxygen. So, because it is a weak nucleophile, now it can easily attack to the carbonyl carbon. Hence, we can also say the electrophilicity of carbon is increased. So, first of all, a tetrahedral product is there, hemiketal, and it is further react to give a ketal. In the same way, nucleophilic addition of this alcohol to the carbonyl carbon with the help of acid. Reaction with thiols, formation of thioacetals. Aldehydes and ketones react with thiols in the presence of acid catalyst to form thioacetals and thioketals respectively. These are also the protecting group as in case of acetals and ketones for aldehydes and ketones. Hence, these are also useful in the synthesis of these compounds. Thioacetal and thioketal formation is useful for the conversion of carbonyl group into methylene group, since carbon sulfur bonds can be replaced by carbon hydrogen bonds by reduction with hydrogen in presence of ranitidine. Thioacetals are also useful for converting an aldehyde to higher ketones by a series of reactions as described below. So, pentane 3-on when reacts with methane thiol, it will give you 3,3-bis methyl mercaptopentane. It is a thiol ketal because sulfur is there. So, these are the another reactions. When pentane 3-on reacts with ethane 1,2-dithiol, it will gives you 2,2-diethyl 1,3-dithiolane, and after reduction it will give you pentane. Acetaldehyde when reacts with propane 1,3-dithiol, it will give you 2-methyl 1,3-dithiolane, and after reaction with ethyl iodide and mercury chloride, it will give you butane 2-on. Next very important reaction is the reaction with phosphorus halide. This is called Wittig reaction, and it is so important reaction given by George Wittig and Herbert Charles Brown, awarded for Nobel Prize in Chemistry in 1979 for their work on developing phosphorus and boron containing compound. What is halide? We are saying it is phosphorus halide. What is halide? Any compound with opposite charges on adjacent covalently bonded atom, each of which has a complete octet of valence electron. Since phosphorus can accommodate more than 8 electrons in the valence shell, a phosphorus halide, also called a phosphorane, you can see in the figure, and has an uncharged resonance structure also, methylene triphenyl phosphorane, or we can also say triphenyl phosphonium methyl halide of phosphorus halide. In the mechanism, how the mechanism proceed? First of all, this phosphorus halide first of all attack to the carbonyl compound, then a butane is formed. You can see in the reaction how butane is formed. This butane then will convert it to oxaphosphetane, and this oxaphosphetane after rearrangement will give you alkene and triphenyl phosphine oxide. How phosphorus halide are prepared? It is prepared by SN2 reaction of an alkyl halide 1 degree or 2 degree with triphenyl phosphine, and then treating the resulting alkyl triphenyl phosphonium halide with a strong base such as butyl lithium, phenyl lithium or sodium hydride. The base then abstract a proton from the carbon atom adjacent to the positively charged phosphorus. In the reaction you can see, first of all, triphenyl phosphine reacts with alkyl halide, that is ethyl bromide in SN2 mechanism. What is SN2? Binuclear substitution nucleophilic, that is attacking and removal will take place simultaneously. You will get the product triphenyl phosphonium bromide with ethyl group, and then a strong base. Here we are taking the butyl lithium. The product will be the ethylene triphenyl phosphorane, yeah, we can say triphenyl phosphonium ethyl halide. In another reaction you can see reaction with acetone. Again, first of all butane will form, then oxaphosphetane, and the alkene here is formed as 2-methyl but2-ene. Reaction with sulfur halides, formation of epoxide. With Wittig reaction we made the product alkene, and in the phosphorus in this reaction sulfur halide the epoxide will form. Aldehydes and ketones reacts with sulfur halides to form epoxides. In the reaction again dimethyl sulfonium methylide attack with carbonyl carbon. You can see in the reaction how it is attached, and then SN2 mechanism will takes place and an epoxide is formed. With cyclohexanone we will get the product cyclohexane carbaldehyde. Thanks, and I will stop here only. Next in the next series of this lecture I will discuss the rest of the reactions of aldehydes and ketones. Thank you so much.
Sure, definitely we would be carrying this session soon, and we would be continuing from where we left today. With this note, thank you ma'am, thank you so very much for giving us such a productive session, and if you have any queries you can mail us at info.cec@nic.in, so that if you have any questions we would love to solve them the next time when Dr. Vandana comes. Thank you ma'am, thank you so very much.